Let's explore energy and utilities analytics. We will cover smart grid data, renewable energy optimization, and demand forecasting. These are key areas where data analysis can make a significant impact. Smart grids generate various types of data. This includes real-time energy consumption, which tells us how much energy is being used at any given moment. We also look at power generation metrics to understand how much energy is being produced. Grid stability indicators help ensure the reliability of the energy supply. Weather and environmental data can influence energy demand and generation. Finally, equipment performance logs provide insights into the health and efficiency of grid components. Let's look at an example of how smart meter data can be processed using Python. First, we import the pandas library as PD and the datetime module. The function process meter data takes a file path as input. It reads the data from a CSV file into a pandas data frame. Then it converts the timestamp column to datetime objects. The data is then grouped by meter ID and hour, and the mean consumption and voltage are calculated for each group. This provides an aggregated view of energy consumption patterns. Renewable energy sources are becoming increasingly important. Solar power generation involves converting sunlight into electricity. Wind energy systems use wind turbines to generate power. Hydroelectric power harnesses the energy of flowing water. Geothermal energy taps into the Earth's internal heat. Each of these sources offers a sustainable alternative to traditional fossil fuels. Efficient energy dispatch is crucial for optimizing resource use. The function optimize energy dispatch takes demand and supply sources as input. It sorts the supply sources based on cost, prioritizing renewable sources. It then allocates energy from the lowest cost sources first, up to their capacity or until the demand is met. The allocated sources and their amounts are then returned. Accurate demand forecasting is essential for managing energy supply and demand. Time series analysis, such as ARIMA, uses historical data to predict future demand. Machine learning models can learn complex patterns from data. Neural networks, especially LSTM, are effective at capturing long-term dependencies. Seasonal decomposition helps identify and isolate seasonal trends. Weather-based prediction incorporates weather data to improve forecast accuracy. Here is an example of how to implement an LSTM neural network for energy forecasting using TensorFlow and Keras. This code defines a sequential model. It includes an LSTM layer with 64 units, set to return sequences for stacking LSTM layers, and expects an input shape of 24 time steps with 5 features. Another LSTM layer with 32 units is added. It then has a dense layer with 16 units and ReLU activation, followed by a final dense layer with 1 unit for the prediction. The model is compiled using the Atom optimizer and mean squared error loss function. The future of energy analytics is full of exciting possibilities. Artificial intelligence-powered optimization can further improve energy efficiency and grid management. Internet of Things or IoT integration and edge computing will enable real-time data collection and analysis at the source. Blockchain energy trading can facilitate peer-to-peer energy transactions and improve transparency. Quantum computing applications may revolutionize energy modeling and optimization. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.